An invisible war rages around us. It's a battle for survival, waged on a microscopic scale. On one side are bacteria, single-celled organisms that inhabit virtually every corner of the Earth. On the other side, bacteriophages. Bacteriophages, or phages for short, are viruses that prey exclusively on bacteria. These microscopic assassins are the most abundant biological entities on the planet, outnumbering bacteria by a factor of 10. They are masters of destruction, honed by evolution to target and eliminate their bacterial prey. Every day, phages destroy trillions upon trillions of bacteria, playing a crucial role in regulating bacterial populations. They are essential to the balance of ecosystems, from the soil beneath our feet to the oceans that surround us. And as we are coming to realize, they may hold the key to combating one of the greatest threats to human health: antibiotic resistance. Phages are remarkably diverse in their shapes and sizes, but they share a common goal: to hijack bacterial cells and turn them into factories for producing more phages. This hostile takeover is a marvel of biological engineering, playing out like a scene from a science fiction thriller. The phage's life cycle begins with attachment. Using specialized proteins, the phage latches onto the surface of a bacterium, anchoring itself like a lunar lander touching down on an alien world. Once attached, the phage injects its genetic material, DNA or RNA, into the bacterium's cytoplasm. Inside the bacterium, the phage's genetic material takes control, reprogramming the cell's machinery to produce phage components instead of its own proteins. The bacterium, now a slave to the phage's commands, churns out new phage particles, assembling them like microscopic robots on a factory floor. Finally, the cell bursts open, releasing a swarm of newly minted phages into the environment, ready to seek out and destroy more bacteria. This process, known as lysis, marks the end of the bacterial cell and the beginning of a new cycle of phage infection. For decades, antibiotics have been our primary weapons in the fight against bacterial infections. These miracle drugs revolutionized medicine, saving countless lives and ushering in an era of unprecedented medical progress. But our reliance on antibiotics has come at a cost. The widespread use and often misuse of antibiotics has driven the evolution of antibiotic resistance. Bacteria, with their remarkable ability to adapt, have developed ways to evade or inactivate the drugs designed to kill them. The result? A growing number of bacterial infections are becoming resistant to the antibiotics we rely on. This rise of antibiotic resistance is a global health crisis. Infections that were once easily treatable are now becoming deadly. The World Health Organization has warned that we are entering a post-antibiotic era where common infections could once again kill. The need for new and effective treatments is more urgent than ever. Section 4, a beacon of hope, phage therapy. In the face of this growing threat, scientists and clinicians are turning to a century-old approach to fighting bacterial infections: phage therapy. Phage therapy harnesses the bacteria-killing power of phages to treat infections, much like antibiotics do. But unlike antibiotics, which are broad-spectrum agents that can harm beneficial bacteria, phages are highly specific. Each type of phage has evolved to infect and kill a specific strain or species of bacteria. This specificity is one of the key advantages of phage therapy. Because phages only target the harmful bacteria, they leave the patient's healthy microbiome intact, reducing the risk of side effects. Phage therapy is not just a theoretical concept, it has a long and storied history dating back to the early 20th century. Before the advent of antibiotics, phages were used to treat a wide range of bacterial infections, with some remarkable successes. Now, with the rise of antibiotic resistance, phage therapy is experiencing a resurgence of interest. Section 5, the future of phage therapy, challenges and opportunities. While phage therapy holds immense promise, several challenges must be addressed before it can become a mainstream treatment option. One challenge is the need for more extensive clinical trials to demonstrate the safety and efficacy of phage therapy in different clinical settings. Another challenge is the development of standardized protocols for phage production, purification, and administration. Unlike antibiotics, which are chemically synthesized, phages are biological entities that require careful handling and storage. Despite these challenges, the future of phage therapy is bright. Research in this field is expanding rapidly, and there is growing investment from both the public and private sectors. Scientists are developing new techniques for phage engineering, allowing them to create phages with enhanced therapeutic properties. The potential of phage therapy to combat antibiotic resistance is enormous. By harnessing the power of these microscopic assassins, we may be able to turn the tide in the fight against superbugs and usher in a new era of infectious disease control.